Welcome to another educational video from Belimo. Today we will look at the benefits of pressure-independent control valves, and the different designs of mechanical and electronic pressure-independent control valves. We are focusing on basic physical laws, they are manufacturer-independent and universally valid. Before we look at pressure-independent valves, I want to start with a quick review of pressure-dependent valves. To do this, I have prepared a sample system. How does a system with pressure-dependent valves work? We see a schematic of a room with a radiator, return and supply pipes, a control and balancing valve, and a room temperature sensor. Several rooms form a large unit. The signals of the room temperatures go to the controller and from the controller to the actuators of the control valves. We fill the system and put it into operation. A control signal is sent from the controller to the rear three rooms. The flow rate is significantly reduced. As you can see, the room temperature in the first room rises, and the room sensor sends an electrical pulse to the controller. A control signal is sent back from the controller to the actuator. This reduces the flow to return the room temperature to the desired range. In the upper left area, we now see a picture. This picture shows the time axis and the temperature rise. After the rear three valves have reduced flow, a temperature increase occurred in the first room. This is overheating and causes extra energy consumption. It can also be said that a pressure-dependent system is never balanced in partial load operation. We'll take a closer look at the implications of this in a later part of this educational video. Now let me explain why pressure-independent valves exist in the first place. First, I would like to discuss the mechanical pressure-independent valves. The advantage of a mechanical pressure-independent valve is to move from a fluctuating pressure to a constant flow rate. Let's take a closer look. What we see here is a cross-section of a mechanical pressure-independent valve. Regardless of the valve manufacturer, the basic design is almost identical. The fluid flows first through an integrated differential pressure controller and then through the regulating device, which I marked with a red circle. The differential pressure controller aims to reduce excessive supply pressure and keep the pressure between P3 and P2 constant, so that the pressure across the regulating device is always constant. How does this work in detail? In particular, we will look at this picture's green and orange areas. Let us now look at our pressure-independent valve at a relatively low supply pressure of, for example, 17 kPa. The low supply pressure ensures that the differential pressure controller allows the opening gap, S, to open slightly so that sufficient water and volumetric flow can pass through the valve. If the minimum supply pressure now increases to 65 kPa, for example, the opening gap, S, is greatly reduced. This means that high supply pressure is automatically relieved. Mechanical pressure-independent valves, therefore, have a significant advantage over pressure-dependent valves. They automatically balance each other hydronically. Additional advantages are a simple and fast valve design. Another advantage is the constant flow of mechanical pressure-independent valves. They independently reduce supply pressures that are too high. They are very compact and have a significantly shorter design compared to a standard control or balancing valve. These valves can be installed or reused with great flexibility in the event of a subsequent conversion or system change. Some things that have advantages also have disadvantages. This is also the case with mechanical pressure-independent valves. One of the biggest disadvantages is the so-called minimum pressure. They are also called minimum supply pressure by some manufacturers. For small valves from DN15 to DN20, this is typically between 15 and 22 kPa, respectively between 1.5 and 2.2 meter water column. However, as we look at the larger valves, we see that the minimum pressure becomes much larger. For DN40, many manufacturers typically exceed 30 kPa, for even larger valves, up to 65 kPa. It is also important to note that flow rate feedback is only possible with calculated values. This, however, only with a low accuracy of at least plus or minus 20%. In most cases, however, the difference is significantly greater. Let's now take a closer look at electronic pressure-independent valves. An electronic pressure-independent valve functions similarly to a mechanical valve. It ensures that the volumetric flow is kept constant at all times, but according to a completely different operating principle. If the differential pressure in a system drops, for example, because several consumers open simultaneously, the volumetric flow also drops automatically. The electronic pressure-independent control valve automatically detects this and simply opens a little further so that the setpoint and actual volumetric flow automatically equalize. If, however, the differential pressure increases in the opposite case, for example, because several consumers close, the volumetric flow also increases automatically. The flow sensor also detects this and automatically acts on the control valve. This closes until the actual and target volume flow is identical in this case. How is such a pressure-independent valve constructed? The electronic pressure-independent valve typically has an ultrasonic flow sensor and a control valve with an electromotive actuator. How does such an ultrasonic flow sensor work? The ultrasonic flow sensor is designed so that the transmitter emits an acoustic signal. The receiver receives this signal and mirrors it back to the transmitter. Thus, the acoustic signal flows once in the direction of water flow and once in the opposite direction. The running speed of the acoustic signal is measured electronically for both directions, and with this information, the flow rate can be calculated with high accuracy. How is a pressure-independent valve system designed? As in the pressure-dependent valve example, we again see the room with the radiator, the supply and return pipes, the installed electronic pressure-independent valve, and the room temperature sensor. The respective room temperature sensor is connected to the controller, which in turn controls the actuators of the control valves. We fill the system and put it into operation. The controller sends a control signal to the rear three valves. These change their value. The actuator at the front automatically detects the change in branch pressure and adjusts its position accordingly. If we look at the picture on the top left, we can see that only the amount of energy that is actually needed is delivered to the room. In summary, I would like to reiterate the advantages of electronic pressure-independent valves. Analogous to the mechanical pressure-independent valves, automatic hydronic balancing is also performed here. A simple and fast valve design is possible. In addition, these valves always guarantee a constant flow rate, which is permanently monitored by the flow sensor. The valve automatically reduces supply pressures that are too high. It controls the volumetric flow very precisely and reports the actual volumetric flow directly back to the building automation. Electronic pressure-independent valves generally have a much lower pressure loss than comparable mechanical pressure-independent valves, especially in the larger dimensions from DN25. Like mechanical valves, electronic pressure-independent valves have the great advantage of being very flexible regarding subsequent changes. And last but not least, glycol measurement and monitoring can also be performed with some electronic pressure-independent valves. By monitoring the glycol content, leakage in a system can be detected, and a fault message sent. I would also like to discuss electronic pressure-independent valves with built-in energy management functions. In addition to the advantages just mentioned, valves with energy management have the following positive characteristics. Output power can also be used as a controlled variable. This allows the valve to regulate to a preset power. The valves thus provide the data basis for an energy evaluation of a system. They provide the basis for a digital twin that can be used to map an entire digital ecosystem. Finally, I would like to mention that MID-certified valves, according to EN 1434, can be used to generate legally valid heating bills. In summary, I would like to reiterate the difference between pressure-independent and pressure-dependent valves. Pressure-independent valves always have a valve authority of 1 due to their design and constant tracking of water flow. Pressure-dependent valves have a valve authority dependent on the pressure loss across the variable flow portion of the circuit. Pressure-independent valves are always perfectly balanced, both for the full load and the part load range. Pressure-dependent valves are only balanced for full load and are correspondingly inaccurate in partial load. Pressure-independent valves perform hydronic balancing automatically, whereas with pressure-dependent valves balancing must be performed manually and using a balancing valve. Extension of the system is typically possible without any problems with pressure-independent valves, without the need for major structural modifications. In the case of pressure-dependent valves, the system must be recalculated when adjusted, and, in most cases, at least the balancing valve must be readjusted. In the worst case, the control valve may need to be replaced to maintain the same high valve authority. Regardless of the manufacturer, pressure-independent valves always have a very broad field of application. The advantage is that one valve can cover many requirements. There is no need to resort to rigid KVS values, as with pressure-dependent valves. The bottom line? As we say at Belimo, small devices, big impact. We are happy to provide you with the application guide as a handout. Scan the QR code to download the document electronically. For more background on pressure-independent valves, see the application guide. I hope this educational video has provided you with some useful information. Thank you for your attention.